colegas. So the next contribution comes from Mexico, from Professor Mauricio Sales-Cruz. He did his PhD at the Technical University of Denmark, and he's professional researcher at the Universidad Autónoma Metropolitana of Malta. He's going to be talking about process intensification of lignocellulosic biorefinery.
Well, thank you very much for the invitation. Thank you, Rafik. Thank you, Professor Shi. Thank you, everyone, so that invite me to come. And then today I'm going to talk about process intensification of lignocellulosic biorefinery. So biorefineries hold promise for converting waste material into valuable products, but face challenges in efficiency and profitability. This study that we developed aims to enhance biorefinery design by integrating operation and analyzing mass and energy integration. A systematic approach that we propose to assess process configuration based in a key criteria such as emissions, utility duty, energy consumption, and cost. Optimal strategies for ethanol biorefinery are identified through diverse configurations, and comparison of pretreatment and separation techniques so show that or highlights the most efficient design and offering insights to improve biorefinery's performance and viability. This is the topic about. So as you know, biorefineries is a facility that use biomass to produce different variety of products, including biofuels. What's happening?
Another point.
This one up and then down. Yes. Yep. Okay. So biorefineries use renewable organic materials such as energy, crops, agricultural, forestry, or food waste. And this biomass serves as the primary raw material, offering a renewable carbon source compared to the non-renewable fossil fuels. One of the key distinctions between biorefineries and conventional refinery is their focus on sustainability and environmental friendliness. Biomass generally has lower environmental impact compared to the fossil fuels, aligning with the biorefinery's goal and adopting more sustainable practices. So, other thing that defines these facilities is a diverse range of products, including liquids, biofuels, green chemistries, biodegradable materials, and other biomass products. The approach underscores the transition towards a more sustainable economy based on renewable resources and constraining the dependence of petroleum products from conventional refineries. So, sustainable design of bioethanol production process through process intensification represent a significant and economically viable approach in the field of bioenergy and renewable fuels. Here, I'm going to show some key issues that point out this topic. Renewable energy source, bioethanol is produced from non-food raw materials. The use of non-food raw materials contributes to the overall sustainability of the bioethanol production process. Reduce environmental impact. Process intensification involves optimizing and utilizing the production process to improve efficiency and minimize resource consumption. Efficiency improvements, process intensification techniques such as advanced reactor design, improved catalyst, and improved process control can significantly increase the overall efficiency of biofuel production. And of course, the use of waste by converting these wastes into bioethanol or into other chemical products. A valuable fuel source is created from materials that may otherwise be considered only waste. And sustainable design often involves the incorporation of cutting-edge technologies like advanced hydrolysis processes, fermentation, and enzymatic separation processes can improve the overall sustainability of the production process. Of course, sustainable economy, this kind of design is used to not only about environmental considerations, also include the economic viability and potential and regulatory landscapes. Means there should be supportive policies, incentives, and clear regulatory framework can encourage to adoption of sustainable practices in bioenergy sector. Integration with circular economy principles, like Mauricio mentioned, so sustainable design must align with the circular economy principles where resources are used efficiently, waste is minimized, and the entire production process is designed to be regenerative. This approach ensures that a more holistic and environmentally friendly bioethanol production system. In general, the sustainable design of bioethanol production process through process intensification represents a promising and holistic approach addressing the environmental, economy, and social aspect of bioenergy production. It aligns with the global effort to transition to cleaner and more sustainable energy sources. So this is why I have organized my presentation. With first I want to talk a little bit about the motivation and, of this work, the objectives, and then the general methodology to use to evaluate the intensified process. Later I will explain a little bit the conceptual design of ethanol biorefinery and focusing on the system and design of the process. And finally, I want to show you the simulation results and summarize my conclusions. So, second generation biorefineries having shown that a potential convert biomass into fuels, energy, and other chemicals, such as amino acids, enzymes, organic acids, antibiotics, among others. In particular, these biorefineries have received more attention due to no competition with food, neutral balances of carbon dioxide, high availability of feedstocks from agro waste, forest waste, energy crops, municipal solid waste, HC, and moreover, these second generation ethanol plants have been built in various countries. Well, however, there is also some challenge in this industry operation because with lagging on economy, mainly due to high operation cost, irregularities in the raw material supply chain, complexity in handling several feedstocks, and low technological maturity and lack of mechanization and automatization strategies, and some scaling up the challenges. Additionally, from the process intensification of industrial process, there are several opportunities to improve this performance. These opportunities that I can mention, well, we can have simplified processes, lower energy consumption, less waste, lower operation costs, higher productivity, greater installed capacity, greater flexibility, and increased safety. But also, process intensification must face barriers. For instance, some challenges to overcome are reliability in mature technology, risks due to lack of precedence, expensive new equipment, concerns about security and control, lack of validated process intensification units, and lack of metrics to perform evaluation. Although several studies have been reported for the evaluation of case studies or from a process intensification perspective, most of them have been conducted in isolation. So then the objective of this work is a proposal for a systematic approach to evaluate different process configuration by defining a global indicators that impact the sustainability of the process, such as reducing the cost to increase profitability, reducing waste to decrease the impact of degradation of ecosystem, and reducing the energy consumption due to the utility duties, such as steam, cooling water, and electricity, while the thing is to mitigate the climate change. In particular, the proposed methodology is exemplified with a case study for a second-generation biorefinery for ethanol production. Well, taking into account different reported approaches to intensify biorefineries, we decided to incorporate four main aspects. First, the integration of unit operations. This is how to make one or more unit operation more compact and efficient and effective with lower acquisition and operating costs. First consider the conceptual design of a second-generation biorefinery as shown in this figure, and where the biorefinery is divided into 5 main steps. Commissioning of the feedstock, where mainly the particle size reduction done, pretreatment, where mainly cellulose is hydrolyzed, and saccharification, where the cellulose is converted mainly into glucose, and fermentation, where the sugars are converted into product and product recovery. And in particular, there are different technologies that allow to join intensification of the saccharification and fermentation stage. One is the separate saccharification and fermentation, and other is to simultaneous saccharification and fermentation processes. And the third case corresponds to the consolidated bioprocess. In fact, this consolidated bioprocessing is the process with the highest degree of intensification. Its application has not reached the maturity to be implemented industrially. So in this work, we select simultaneous saccharification and co-fermentation. Well, second is mass integration. So that offers promising opportunities in terms of recovery and recycling of some raw materials. Some potential modules that could be incorporated into intensified biorefinery are cogeneration module, where solid waste is born for production of electricity and steam. Lignin recovery, so that lignin can be used in other specialized applications. Wastewater treatment to remove pollutants and recycling processed water, and capture and purification of CO2 to reduce greenhouse gases in their subsequently reuse. And third, the heat integration, which is a fundamental part of process design and synthesis, as it has implication for energy consumption, operating costs, and environmental impact. Here, maximum energy recovery should be determined using a systematic methodology based on the thermodynamic principles such as energy pinch analysis. And fourth, the evaluation of the intensification objectives. Here, having in mind that an intensified process is a simpler, or should be a simpler, safer, cheaper, cleaner in terms of waste and more energy efficiency processes. For this purpose, three evaluation criteria are defined to measure. First, the production cost with this economic evaluation, the energy consumption with energy evaluation indicator, and the waste generation. And then we can combine all together to have the global intensification criterion that could be used for decision making of the biorefinery design, maintaining a balance between these three aspects. So let me show briefly how we define these key indicators to obtain this global criteria. First, the economic evaluation to profitability analysis can be performed based on the profitability ratios or discount cash flow ratios. And here the unit production cost, Y1, this is the first one, the first indicator is determined from the method of net present value equal to 0, assuming a constant interest rate. Therefore, the lower production cost means the higher profitability. Then the energy evaluation. So the net energy consumption comes from duties like heating, cooling, and electricity required by the process, subtracting the integrated heat and the electricity generated. So we define the energy consumption yield, Y2, as the net rate of energy consumed divided by the production rate of the main product. So the lower the energy consumption yield means the higher the energy efficiency. Then for the third indicator for the waste evaluation, the main streams of pollutants are wastewater, solid residues, and greenhouse gases, mainly CO2, produced in the stage where the fermentation or combustion reactors occur. Therefore, to calculate the waste yield, Y3, the cumulative rate of waste divided by the production rate of main product. So, in this way, the lower the waste yield is, the less environmental pollution. And finally, for the global intensification, so we combine all together, and due to the multi-objective nature of this process intensification, all indicators are compared and weighed against each other to evaluate different process configurations and decide which of these presents the best performance. Thus, the global intensification criterion is calculated according to this equation. I don't know why it's not correct, but it's really bad. Well, this is assumed as a weighting assumed to the indicators, normalized by the biggest one in each state. So, and this is the lower global criterion, the greater the intensification and performance of the global process. So I want to show this methodology applying to this conceptual design of ethanol production. We select this as a case study because there are major technology for the industrial process involved, and there are also efficient and robust enzymes and microorganisms to transform sugars into ethanol. For the conceptual design, we consider the main species shown in a previous slide, so we are here. Put it all together. And taking into account the intensified reaction, that is the simultaneous saccharification and co-fermentation. And we are particularly interested in the analysis and comparison of two different parameters and two separation processes. The first one is to dilute acid pretreatment and steam explosion pretreatment. we select, these two are reported to be the most efficient. While to the separation process, we have select absorption with the molecular sieve and extracted distillation for the degradation of ethanol due to the fact that this is a process that have achieved lower energy consumption. Okay, in addition to optional modules are incorporated. So as well, we define this composition of the feedstock that comes from sugarcane bagasse. And then from the cellulose, 47%, 29% on cellulose, and 44% lignin, and 9.6 for other solids. And then for analysis of comparison of these, we define 4 base cases with the P1 is 1 is pretreatment 1 is a derivative acid pretreatment, P2 is steam explosion pretreatment, and S1 and S2 two different separation techniques like separation with molecular sieves and separation with extractive distillation. And then we propose 4 intensified processes with wastewater treatment like P1 is 1W and so on, and cases with wastewater treatment and together with cogeneration. So we have in total 24 configurations are defined, and all these configurations we can simulate and test. For that, so we propose a simulation to this biorefinery with 330,000 tons of feedstock and the annual capacity of 120 million liters for ethanol to produce, and the evaluation of the intensified objectives were performed in several simulations. So we perform a unit solution cost in Excel, energy consumption in SuperPro Science Simulator, energy analysis in Hint software, and energy consumption yield in Excel, and the waste yield in SuperPro Designer. So here we have the evaluation of the first criteria. This figure presents the unit production cost for all configuration. So I'm going to present for all configuration each indicator that we define, and this is the economic evaluation. And from these results, so we can see that the best case with the lowest cost is P2 is 1 WCH with 30 cents per liter of ethanol. And the second one is P2S2 WCH with 40 cents per liter of ethanol. In fact, we can compare, and we have a reduced, comparing with the base case, reducing of 55% of cost. In terms of energy evaluation, we perform the same, and then we found that P1 is 1 is the best, followed by the P1 is 2, and we have a reduction of 60%. Well, the third one evaluation is waste reduction cost. So we can find this the best case at lowest generation of the waste, the P2S1 and P2S2 to reduce the CO2 emissions. So by incorporating the wastewater treatment module, so water consumption dropped 55% in total. So, but there is no significant difference when comparing pretreatment or separation part. Well, now we combine with all three to the global integration criterion, first to taking the same weight for each indicator, and then for here we have again that P1 is 1 is the best, and if we increase or we put more weight to the economic key criteria, so here as well P1 is 1 is the best cost. And we do the same, so just moving the different ways to have different scenarios to found that these processes are one of the best. We found 2, P1 is 1 WCH, and P2 is 2 with WCH. And with that, just let me finish summarizing this IP methodology that we propose. We believe that PWAS addresses using intensification aspect like integration of unit operation, mass integration, heat integration and evaluation of all the intensification indicators together. So with this economical intensification criterion was defined incorporating weighting of economic criterion, energy consumption, and residual criterion. So we can find that the best intensified solution was with the pretreatment one, separation technique one, with water treatment and heat integration and confederation. So the best pretreatment is uric acid, and the best separation is molecular sieves, and is very close to extractive distillation. And with that, I want to take to you for free here, and I want to acknowledge to Professor Teresa Lopez and PhD graduate Moises Gonzalez. Thank you very much.